Okay, so we just talked about some mechanisms by which we can reabsorb molecules into our bloodstream from the tubule lumen. But what I'd like to point out now is that that process can reach a saturation point. So that's what's illustrated here in this graph. What you are looking at here on the x-axis is the plasma concentration of the substrate. So the substrate is the solute that we are trying to reabsorb, okay? That is proportional to the concentration of the substrate in the filtrate, right? So that's what's on the x-axis. On the y-axis, we have the transport rate of the substrate. So the rate at which it's being reabsorbed into the body, okay? And what you can see here in this graph is that as we increase our plasma concentration or our filtrate concentration of our substrate, the transport rate is going to increase along with that until we reach a point right here where saturation occurs, okay? Then we reach a plateau. So what's happening here at this saturation point? What is happening is that our transporters that are transporting those molecules are all saturated, right? So every single transporter is in the process of transporting one of these substrate molecules. And once we reach that point, no matter how many substrate molecules we have, we can't get any faster than this. We can't transport them any faster than this rate. Okay, so hopefully that was clear to you. We have a couple terms here. Okay, so the maximum rate at which we can reabsorb a molecule is called the transport maximum, or T sub m. Okay, so that's the rate at which we can transport when we are saturated. The other term we have here is the renal threshold, which is the plasma concentration of the substrate at which that saturation occurs, okay? Here's a question for you. What is going to happen to these materials that don't get transported, right? So let's say we have a high concentration of our substrate in the filtrate, and it's so high that we can't transport all of it. What's going to happen to it? Think about that for a second. Okay, so hopefully you figured out that anything that we don't reabsorb is going to end up being excreted in the urine, okay? So for substances that we want to reabsorb, that's not good because we don't want to lose those precious substances. Okay, so here is a specific example of this situation using glucose transport. So what you're looking at on the left here, this graph is basically that same graph that you saw in the previous slide, but it's specific for glucose, right? So we're looking at specific plasma glucose concentrations. As we increase our plasma glucose concentration, we increase the rate at which we reabsorb glucose until we reach our renal threshold, okay? Once we reach our renal threshold, then we reach our transport maximum, and any extra glucose, right? So once we get to higher glucose concentrations, that extra glucose is going to get excreted in our urine, okay? For most people, this isn't a problem because usually people's plasma glucose concentrations are in this range, right? So it's in the range where we're going to end up reabsorbing all of the glucose that we filter into our tubule. However, for diabetics who have high glucose concentrations, they're going to be in this range here, and they're going to end up losing some of their glucose to their urine. Okay, and this actually is the sort of the origin of the term diabetes. So diabetes, the full name for diabetes is diabetes mellitus. Mellitus means sweet, okay? And that sweet characterization comes from the presence of glucose in the urine. So they used to diagnose diabetes by tasting the urine of individuals. And if it tasted sweet, then that was an indication that you had a high plasma glucose concentration, so high that you couldn't reabsorb it all and that it ended up in your urine. Okay. So that actually was a privilege given to aspiring physicians. So those of you who are aspiring physicians now, you can lament the fact that you have missed out on that opportunity, although I guess you could always reproduce it yourself. So they don't do that anymore, but essentially they do. So, I mean, without tasting the urine, we now use dipsticks to test for the presence of glucose in the urine, and that is an indicator of diabetes. Okay, enough of that. Okay, so I want to close this discussion of transport maximum with this slide here. Remember that I introduced this mathematical relationship to you where I showed you that the amount of solute that we excrete is equal to the amount that we filter minus the amount we reabsorb plus the amount we secrete. We can actually do that calculation in graphical form, right? So what we're looking at here is filtration rate of glucose, okay, relative to plasma glucose concentration. If we take that and we subtract the reabsorption rate of glucose from this graph, so we're taking this graph minus this graph, then we end up with this graph here, which shows you the excretion rate of glucose, okay? Another way to think about this is that once your filtration rate gets above your reabsorption rate, that's when you start to see glucose being excreted. Okay, so there's one last thing that I want to address with reabsorption, which is that our discussion of reabsorption so far has focused on the process of getting materials back into this extracellular fluid from the tubule lumen, right? We've really just focused on getting materials across this wall here. However, what we really want is we want to then get those materials into our peritubular capillaries so that they can re-enter our circulation. So how is that done? How do we get fluid back into the peritubular capillaries? Well, it turns out that that's actually a very easy problem to solve because colloid osmotic pressure is much greater than the hydrostatic pressure in the peritubular capillaries. So we naturally reabsorb. We have a net reabsorption pressure, basically, of 20 millimeters of mercury. So we're going to end up reabsorbing fluid into the peritubular capillaries. Piece of cake.